Assalamu alaikum everyone. I hope you're having a great day. Today we are going to take an in-depth look at the most recent Edexcel A-Level Physics Unit 5 paper from June 2025. So without further ado, let's dive right in. Let's start with section A, question number 1. Which of the following statements applies to both electric fields and gravitational fields? Each field causes a force on all particles. No. Electric field do not exert force on all particles. Electric fields only exert force on charged particles, not all the particles. So A cannot be our answer. B says each field can cause an attractive or repulsive force. No. Gravitational field never ever exert repulsive forces. Field strength is proportional to the square of the distance from a point source. No. Field strength is inversely proportional to the square of the distance. That's why answer is going to be D, because we know F is equals to KQ1 Q2 divided by R squared. So this force is inversely proportional to the square of the radius. And C is not correct. It says proportional, but actually it's inversely proportional. The question 2 says a mass is driven into oscillation and resonance takes place. Which of the following statement is not correct? It's very important. Sometimes the students don't pay attention right here and they just tick which is correct. You will have to make sure that you tick the option which is not correct. The amplitude of oscillation is maximum. Yeah, it's correct. When resonance takes place, the amplitude of oscillation is maximum because maximum transfer of energy occurs. And that's why D is also the correct answer. And C is the mass is driven at its natural frequency. Yes, resonance only takes place when the mass is driven at its natural frequency. So it's a correct answer as well. So definitely B is going to be the option which is not correct and it's going to be our answer. But let's see what it is actually. It says the frequency of oscillation of the mass is maximum. No, there is nothing like that at maximum frequency resonance will occur. No, resonance will occur when the frequency at which the mass is driven is equal to the natural frequency of the mass. So, option B is the only option which is incorrect. Now, the question number 3 says energy is released when the fusion of low mass nuclei takes place. Energy is also released when the fusion of high mass nuclei takes place. So, guys, you'll have to see one thing, that is, the energy is released in either ways. This is fusion and this is fission reaction. Which row of the table shows the change in binding energy per nucleon? Now guys, the binding energy per nucleon increases whenever the energy is released, right? So in both the ways energy is released. So that means the binding energy is going to increase no matter whether it is a nuclear fusion reaction or a fission reaction. That's why our answer is going to be D. Now in the question number 4 it says a megaparsec is a unit of distance used by astronomers. 1 megaparsec is 3.1 into 10 to the power 22 meter. Very good. Recent estimates of the Hubble constant gives a value of 74 kilometer per second per megaparsec. Which of the following gives the age of the universe in seconds? Now guys, we know 1 divided by h naught is equals to the age of the universe, right? Now here let's figure out the h naught. They have said the Hubble constant gives a value of this. This is the Hubble constant. So Hubble's constant is equals to 74. This is kilometer. So we can convert this kilometer into meter by multiplying it with 1000. And now it becomes meter per sec MPC minus 1. So this MPC minus 1. So guys, what does this minus 1 means? This minus 1 means 74 into 1000 meter per second divided by mega per sec. Okay, and we know this mega per sec is 3.1 into 10 to the power 22. So the value becomes 74 into 10 to the power 3 divided by 3.1 into 10 to the power 22. This is my Hubble's constant. And we will have to figure out the age of the universe. And the age of the universe is inverse of Hubble's constant. So we will just have to take it upward and this downward. So the answer is D. On Earth, hydrogen is observed to emit a spectral line with a wavelength of 410 nanometer. The same spectral line is observed in the radiation received from a galaxy that is moving away from the Earth at speed 0.1 c. Which of the following is the wavelength of the spectral line in the radiation received from the galaxy? Now guys, for this type of question, the formula is del lambda by lambda is equals to V by C, right? Wavelength observed minus emitted divided by emitted is equals to V by C. Now right here, we know that the speed is 0.1 c, right? So we can write 0.1 c divided by c. So this c gets cancelled out. And if you write about del lambda by lambda, lambda observed is something that we'll figure out, minus the lambda emitted is basically 410, right? Divided by 410. This is basically the wavelength of the hydrogen in the earth. Okay, so from here I'll have to make this lambda naught the subject, and if we make it, we will get the value as 451 nanometer, and that's why A is our correct answer. The question number 6 says, in a laboratory the background count rate is 22 counts per minute. Alright, so it's 22 counts. A detector is placed 25 centimeter from a gamma source. The count rate recorded by the detector is 54 counts per minute. So this is basically the overall count rate. The detector is then placed 50 centimeter from the source. So now he has basically increased the distance. Now guys, we know one thing, that intensity is directly proportional to 1 divided by d squared, right? So if you increase the distance, the intensity is definitely going to decrease, right? So the counts are going to definitely decrease. Which of the following is the expected number of counts per minute? So guys, now they are asking us the number of counts per minute. Okay, all right, so here we'll have to see one thing, that is 54 was the count rate, and we know the background count rate is 22, right? So let's figure out the actual counts that is incident on the detector, the actual counts that is incident on the detector. So it is going to be 54 minus 22. This was for 25 centimeter, but in the next scenario they have basically doubled the distance. So guys, let's say intensity is directly proportional to 1 divided by 1 square. At that time intensity is equals to 1 divided by 1, right? But now if I double this distance, so intensity is directly proportional to 1 divided by 2 squared. So what does it become? It becomes intensity is equals to 1 divided by 4. So the intensity has become 1/4. So now what actually mean is the count rate incident on the detector will become 1/4. So this is basically the general count rate. But when the distance has increased from 25 centimeter to 50 centimeter, now this count rate will be 1/4. Why? Because the distance has doubled. Okay. Now this is basically the count that is incident on the detector. But the question didn't ask us to give the count that is incident on the detector. They have said the total number of counts per minute. So the total number of counts per minute basically means we will actually have to add the background count rate as well, which was 22. So our correct answer is definitely going to be B. Now a question might pop into your brain, that why did I subtract 22 from the total count rate and then divided it by 4, and then why did I actually added the 22 right here? I mean, the question can be like that, if you have to add this 2022, then why did you subtract it initially? The reason is because right here my main job is to figure out the actual count rate that is the detector detecting. Okay, and then I will divide it by 4, because when you increase the distance of the detector from the source, at that time the detection gets reduced, not the background count rate. So that's why I was right here trying to figure out the actual number of detection that happened at 25 centimeter to make it 1/4 when the distance of the detector from the source doubled. Okay, and then I did add the actual background count rate, because the question asked us to give the number of counts per minute. They didn't ask us to give the detection count, they asked us to give the expected number of counts, which basically includes the background count rate. So right here, if I just kept it like this and I didn't add this 2022, that basically means that you have done 1/4 of the background count rate as well. The background count rate is not going to become 1/4 due to the increase in the distance from the detector to the source. Okay, the background count rate is going to remain the same. That's why I have added the background count rate. Now in question number 7, it says a student used a detector to determine the intensity of radiation from a source of gamma radiation. After correcting for background count rate, the intensity of radiation recorded by the detector was I naught. Alright. A lead sheet of 2.5 centimeter was placed between the source and the detector. The corrected intensity of radiation recorded by the detector was 0.5 I naught. The original lead sheet was replaced by a new lead sheet of thickness 7.5 centimeter. Good. Which of the following was the corrected intensity of gamma radiation recorded by the detector? Now guys, we can use this formula, which is I is equals to I naught e to the power of minus mu x, right? Now we can see one thing, that is the I naught has become 0.5 for 2.5 centimeter, right? So we can write 0.5 I naught is equals to I naught e to the power of minus mu into 2.5, right? So from there we can replace both of this I naught and it becomes 0.5 is equals to, sorry, ln 0.5 is equals to minus mu into 2.5. And from there, if we figure out the value of mu, it is basically 0.2772 centimeter minus 1. So this is basically my value of mu. Now using this value of mu, I can easily figure out the new I naught value. So let's do that. I is equals to I naught e to the power of minus mu, which is 0.2772 multiplied by the x, and now the x is 7.5 centimeter, so it's 7.5. So guys, now we can just do one thing, that is I is equals to I naught. We will put this whole thing into calculator and we will see that the value that is coming is basically 0.13. So we can say that the new I is basically 0.13 I naught. So that's why our correct answer is definitely going to be C. The question number 8 says X and Y have the same luminosity. The graph shows the intensity of radiation received at Earth from star X and star Y varies with wavelength. Which of the following statements can be deduced from the graph? Now guys, in order to answer this question, we will actually have to recall the Wien's law. The Wien's law basically says that lambda max is inversely proportional to the temperature, right? Now, right here, what is basically the lambda max is? The lambda max is basically the wavelength value at which maximum intensity occurs. Okay, so this is the point at which the maximum intensity occurs, right? And this is also the point at which the maximum intensity occurs. So let's figure out the corresponding wavelength values for them. So this is the corresponding wavelength value, and this is also the corresponding wavelength value. Now guys, you can see the wavelength value for y is greater than the wavelength value for x, or in other words, the wavelength value of x is small. So if the wavelength value, I mean if the lambda max of x is smaller, then the temperature of x is going to be greater, right? The temperature of X is going to be greater than the temperature of Y. That is what we have understood from here. So now let's have a look at the options. The option A says star X has a higher surface temperature. Yeah, we know that it has high surface temperature than Y. And it says is closer than star Y. So they are basically comparing the closeness as well. So basically guys, we all know that if this is the sun, then the sun has a constant luminosity. If you are right here, you are going to get greater intensity compared to someone who is right here, because he is way more distant than the sun. So the closer you are to the sun, the greater the intensity you are going to have. Now we can see that X has a very high intensity value. That means the X is closer to the sun compared to the Y. So the option A says star X has a higher surface temperature. Yeah, it has a higher surface temperature and is closer than star Y from the sun. So that's why our answer is going to be A. In question number 9, it basically says the graph shows how the displacement varies with time for an object performing simple harmonic motion. Four graphs of a quantity plotted against time for the same period of time are shown below. Now guys, I have a very easy method to solve this type of questions. So let's draw it like this. Sine, cos, minus sine, minus cos. Okay. Whenever we move in this direction, we differentiate, right? And for integration, we move like this, the opposite direction. So now the graph that they have given us is basically a minus cos graph, right? It's a minus cos graph. It is a minus cos graph. And this is the displacement time graph. The displacement time graph is a minus cos graph, and they have asked us to figure out the velocity. Now, from displacement, if you have to move to velocity, we know we'll have to differentiate, right? If you differentiate displacement, you can go towards velocity. Now, right here, you will also differentiate this minus cos. So guys, we know that whenever we differentiate, we're going to move like this. So the differentiation of this graph is going to be a sine graph, because this graph is a minus cos graph and the differentiation of minus cos is sine. And right here, the option D is the correct answer because it is a sine graph. So I'm going to take option D. Now in question 10, they says which graph shows the acceleration of the object varies with time t. Now to figure out the acceleration, we'll have to differentiate the displacement twice, right? If you differentiate the displacement once, it becomes velocity, and then if you further differentiate it, it becomes the acceleration. So right here, you will have to differentiate it twice. So if you differentiate minus cos once, it becomes a sine graph. And if you differentiate it twice, it becomes a cos graph. So the cos graph is basically A, right? This is basically the cos graph. So our correct answer of question number 10 is going to be A. The question number 11 says the photograph shows a woman making a bungee jump. The woman was attached to a platform high above the ground by an elastic rope. So yeah, I can see the elastic rope. Hopefully you guys can see as well right here. After reaching the lowest point of the bungee jump, the woman oscillated with simple harmonic motion of 1.5 second. The woman returned to the platform to repeat the bungee jump. So she is now going to repeat the bungee jump. She was fastened to a second person. The same elastic rope was used for the bungee jump. Now guys, here is a very important part. That is, it says the same elastic rope. The same elastic rope basically means that the stiffness constant is going to be the same. Though previously she did the bungee jump only herself, but now she will be doing the bungee jump with another person. I mean, the second person was fastened with her. Okay. So the mass will be greater, right? The mass on this rope will be greater because previously only the woman was right here. But now, along with the women, there is another second person as well who has been fastened with this woman. So the mass is going to be greater, but the stiffness constant is going to be the same because it's the same elastic rope. After reaching the lowest point of the bungee jump, the two people oscillated with simple harmonic motion. All right. calculate the period of oscillation of the two people. So now they're basically asking us to calculate the period of oscillation of the second bungee jump, but they have given us the period of oscillation of the first bungee jump. So we know that the formula of time period is equals to 2 pi into root over mass by k, right? Now we know in the first jump there was only the women, so we also know the time period as well, so we can easily figure out the value of k, right? Because we know the time period, we know the mass of women, so like this we can easily figure out the value of k. But right now what I'm going to do is I'm going to square this time period. Look at this. So I have just squared the time period. So when you square the time period, you will have to square this whole portion as well. So I've squared the whole portion right here. And then it becomes t square is equals to 2 pi square, basically means 4 pi square. And this root over gets cancelled out. So it's mass by k. Okay. And then from here, I can easily figure out the value of k. So that's how I figured the value of k, which has come as 1176 Newton per meter. Now I know that this k is going to be the same because when the woman was doing the first bungee jump, the elastic rope was used, and that same elastic rope was also used when there was two person. Okay, now to figure out the time period, I will use this formula again, but right now as there is 2% right here, so I'm going to add both of their mass. In this formula I'm going to add both of their mass, and I'm going to figure out the time period. The k value is going to be the same because it was the same elastic rope. So here you guys can see I've added both of their mass, and now the time period has come as 2.16 second. So my final answer is going to be 2.2 seconds. That's it. The photograph shows a student observing the track of alpha particles and beta particles in a cloud chamber. The particles ionize the air as they pass through the cloud chamber. Liquid droplets form around the ions, and the droplets form visible tracks. Okay, so we know that when particles ionize air, tracks are formed, right? This is basically what they have said right here. In the next part, it says the alpha particle tracks are thick and straight. The beta particles track are thin and twisted. It's a very important part. Why the beta particles are twisted? We will look onto it later on. Now let's move forward to the question. The student gives the following explanation for the appearance of the tracks. The alpha particle tracks are thick because the alpha particles are massive particles. No, that's not basically correct. The alpha particle tracks are thick because they are highly ionizing. Okay, that's the main reason behind the tracks being very thick for the alpha particles. And here you can see it says the tracks are straight because the alpha particles are highly ionizing. No, this is wrong. The tracks are straight because the alpha particles are massive. Okay, the massive particles deflect less. The massive particles deflect less. That's why they are straight. The beta particles cause a similar amount of ionization as the alpha particles. No, the beta particles are less ionizing than alpha particles. So the amount of ionization by the beta particles will be less than the alpha particle. Now the next part it says the beta particle tracks are thin and twisted because beta particles are much less massive than alpha particles. Yes, it's true that beta tracks are twisted because the beta particles have a smaller mass, or we can say they are less massive. The beta tracks are thin because beta particles are not very ionizing. So these are basically all our points. Okay, and this is also very important that beta particles cause less ionization than alpha particle, and this is what they asked us to criticize, and we did criticize right here. And this is exactly the same type of question which did come a couple of years back as well. This was basically the question. Okay, and the question that did come in June 25 was basically from these 2 points. There are extra 2 points that I want you guys to understand. That is, if all the tracks are about the same length, that basically means that the particles have similar energy. Okay, now let's say a particle with kinetic energy of 50 joule. will be moving. Now when it will move, let's say if it's an alpha particle, it will ionize a lot. So his, let's say his length will be like this. Now the same alpha particle with an energy of 100 joule will travel a little more. Why? Because it has more energy, it will be able to penetrate more. This was basically the question which we were basically talking. So you can actually look at this question. So yeah, that's it. A satellite of mass 6.5 into 10 to the power 3 kg is initially at the surface of the Earth. The satellite is launched into a circular orbit of radius 4.22 into 10 to the power 7 meter. Calculate the change in gravitational potential energy of the satellite. The mass of the Earth has been given and the radius of the Earth has been given. So guys, this is a very common question in Edexcel A-Level Physics Unit 5. And I actually solved this question in a very easy way, which I'm going to show you right now. So guys, now let's understand this concept. We know gravitational potential is equals to gravitational potential energy per unit mass. And if you make gravitational potential the subject of the equation, it becomes gravitational potential energy is equals to gravitational potential multiplied by the mass. And we know the formula of gravitational potential is minus gm by r. And if you multiply it with this mass, it is minus gmm by r. This is basically the gravitational potential energy value that a satellite has when it is at the surface of the Earth. Okay? And from the surface of the Earth towards the center of the Earth, this is the radius of the satellite. Right? Now, let's say I have launched the satellite from the surface of the Earth to a higher orbit. Let's say right here. So it has moved from this position to this position. Now, when it has moved from this position to this position, definitely, I mean, there will be a change in the gravitational potential energy. Okay, there will definitely be a change in the gravitational potential energy. Now, previously when it was right here, at that time the radius was this much, which is this r. And now you guys can see h is written right here. This h basically means the distance from the surface of the Earth to the orbit to which the satellite has been launched. So this is basically my h. Now, when the satellite is at a higher orbit right here, if you have to figure out the radius of the satellite from the center of the Earth, this is basically the radius. And that radius includes this h plus this r. Okay, so our gravitational potential energy at the orbit, I mean right here, is going to be minus gmm but r plus h. At the surface it was only r because this was the radius, but right now when it is right here, the radius has become r plus h. So that's why it is minus gmm by r plus h. And now here, as we are going to figure out the change in gravitational potential energy, so this is the final destination and this was his initial destination, right? So the change in gravitational potential energy will be final gravitational potential energy minus the initial gravitational potential energy. So here I have written final gravitational potential energy minus initial gravitational potential energy. So the orbit was the final gravitational potential energy minus the surface, I mean the gravitational potential energy at the surface. If you reconstruct them, this is the formula that comes. Hopefully you guys have understood that part. Now let's apply exactly the same formula right here. Okay, so the change in gravitational potential energy is going to be minus gmm by r plus h plus gmm by r. Now here you can see r plus h is written. This r plus h basically means the radius of the Earth plus the distance from the surface of the Earth to the circular orbit. Okay, now right here they have given us that distance together, the radius of the circular orbit. So basically this radius basically includes both the r plus h, and this radius is basically this r. Okay, now let's put all the values right here. This bigger m is going to be the mass of the Earth and this smaller m is going to be the mass of the satellite. Now let's put all the values right here just like the way the formula is, and the answer is minus 3.46 into 10 to the power 11 joule. Now the later part of the question number 13 says the satellite is in orbit above the equator. Deduce whether the satellite would appear to be stationary above the surface of the Earth. Now guys, this is a very important part. We know it takes 24 hours for the Earth to rotate on its own axis, right? Or The period of rotation of Earth about its axis is given as 8.64 into 10 to the power 4 seconds. So this is basically the time that the Earth takes to rotate about its own axis. Now, the satellite with which we are working, if it takes exactly the same time, just like the Earth, then it will seem like that the satellite is stationary. But if it takes less or more time compared to the Earth, then it will look like it is not stationary. So I've written the explanation right here that the Earth takes 24 hours to rotate once. If an object also takes 24 hours to go around Earth, it looks stationary. If it takes more or less than 24 hours, it will not be stationary. Okay. So that is basically how the thing works. Now let's figure out the time period of rotation of this satellite. Now we will actually have to derive a formula. We know when the satellite will be moving around the Earth, at that time it will be moving in a circular motion, right? And who is basically providing that circular motion? The gravitational force is basically providing the necessary centripetal force to the satellite for it to move in a circle around the Earth, right? So we can say that gravitational force is equals to the centripetal force. So we can write the formula gmm by r squared is equals to mv square by r, because gmm by r squared is basically my gravitational force, which is equals to the centripetal force, right? Now let's make v square the subject of the equation. So if we make v square the subject of the equation, it becomes v square is equals to gm by r, and we have removed both of this mass and we have removed one of the radius from both the parts. Okay, now we know one thing, that speed is equals to distance divided by time taken, right? Now when the satellite is revolving around the Earth, at that time is covering this distance, and we know this is the circumference of the circle, right? And the circumference of the circle is 2 pi r. So this is the distance that he is covering divided by time. So we can say that v is equals to 2 pi r divided by time, right? Now here in this equation it was v square. So let's square this part. So if you square this v, this 2 pi r divided by time needs to be also squared. So it becomes 4 pi r squared divided by t square, which is basically equal to the gm by r, because if this becomes v square, which is basically this is the same v square, which is equal to gm by r. That's why we have written gm by r right here. And from here we can make t square the subject of the equation. If we make t square the subject of the equation, we can easily figure out the time taken for the satellite to rotate once around the Earth, right? So that's how this is the formula that will look like. This is the formula with which we are going to figure out that time. And that is basically how we do it. T square is equals to 4 pi square into r cube divided by gm. And if you make t the subject, at that time, the time that is coming is 8.62 into 10 to the power 4 seconds, which is very similar to 8.64 into 10 to the power 4 seconds. So now we are going to write, yes, it will appear stationary above the Earth's surface, because the time that the Earth takes to rotate about its own axis is exactly the time that the satellite takes to rotate around the Earth. The question number 14 says, astronomers use a variety of methods to determine the distance to astronomical objects. Explain why trigonometric parallax can only be used to determine the distance to objects that are relatively close to the Earth. Yeah, guys, it's true that using trigonometric parallax, you cannot measure the distance to distant objects. Now let's understand why. Now guys, here you can see a typical drawing using which we can actually figure out the angle, right? This is basically the angle. Now the nearby star was right here. The nearby star was right here. So you can easily figure out this angle. But now if the star wasn't right here, if the star was a distant object, now let's say the star was this far away. Now if the star is this far away, let's figure out the angle. So here you guys can see how smaller the angle is, guys. How smaller the angle is. Here the angle is so very small compared to this. The more distant the star will be, the smaller this angle is going to be. And it is very difficult to read this angle. Okay, so here our answer is going to be that the parallax angle decreases the further the object is from the Earth. and the angle is too small and can be read from the scale. And another thing, that is the percentage uncertainty is going to be very high, because we know percentage uncertainty is equals to uncertainty divided by average measured value into 100%. The measuring device is going to be the same, so the uncertainty is going to be the same. But as the measured value is very low, that means the percentage uncertainty is going to be very high. The question number B says, for objects that are not close to the earth, the method of standard candles is used. State what is meant by a standard candle. Now guys, we all know standard candles are stellar objects of known luminosity, right? We know their luminosity value. In the later part it says, describe how the method of standard candles is used to determine the distance to a distant star cluster. Now guys, we'll have to actually use the formula intensity is equals to luminosity divided by 4 pi d square. Okay. Now we know one thing very well, that we know the luminosity of the standard candle, right? We know this luminosity. Now to calculate this distance, we'll have to actually measure the intensity of that stellar object on the earth. Okay, the intensity of the stellar object on the earth needs to be measured. And if we are able to measure this intensity of the stellar object on the earth, and we already know the luminosity of the stellar object, we can easily calculate the distance to a distant star cluster. Okay, so this is going to be the 3 points. Standard candles is located in the star cluster. We'll actually have to locate the standard candle first, and then the intensity of radiation received from the candle is measured on earth. Inverse square law, this formula will be used to determine the distance to the star cluster. The question number 15 says, the body of a racing car is connected to the wheels of the racing car by a suspension system as shown. When the body of the racing car is displaced vertically from its equilibrium position, the suspension system causes the car to oscillate with simple harmonic motion. State the conditions for an object to oscillate with simple harmonic motion. This is a very common question. So now guys, what I'm going to do is I'm going to displace the mass. Okay. So yeah, I have displaced the mass and it is oscillating. So I can show you one thing. That is, the more it displaces, the more the acceleration value increases. Look at this. Right here, the more displaces, the more acceleration. Look at this, how bigger the acceleration value is. And now it becomes even more bigger. And now it becomes even more bigger. And when it is coming closer to the equilibrium position, you will see that the acceleration value is decreasing. When the displacement decreases, when it is coming towards the equilibrium position, at that time the displacement decreases. And as the displacement decreases, the acceleration arrow will also decrease. Look at this. As it is coming down, the acceleration arrow is decreasing. Now look at this. The more it will displace from the equilibrium position towards the right hand side, the more will the acceleration value increase. Look at this. Look at this, how it is increasing. Can you see? The more it displaces, the more the acceleration value increases. And another thing is, the acceleration is acting towards the equilibrium position, no matter whether it is displaced or oscillated in the left hand side or on the right hand side. While it is in the right hand side, you can see the acceleration is acting towards the equilibrium position, right? And you will also see the same thing. Look at this. Now when it is displaced in the left hand side, in exactly the same way, the acceleration is acting towards the equilibrium position. And that is the same for both force and acceleration. Now as we all know that force is directly proportional to the displacement from the equilibrium position, and force always acts towards the equilibrium position, right? That is basically the two conditions for the object to oscillate with simple harmonic motion. The graph shows how the vertical displacement of the car body varies with time t. So this is basically the displacement in the y-axis and the time in the x-axis. Now in the actual question, they have asked us to figure out the maximum velocity of the car body. Now guys, we all know that velocity is equals to displacement divided by time taken, right? And they have given us displacement in the y-axis and time in the x-axis. So the gradient of this graph is going to give us the velocity, right? And you have to remember one thing, that they have asked us to calculate the maximum velocity, and the maximum velocity will be occurring at the steepest region of the displacement time graph, and this is basically the steepest region, right? So this is going to be my straight line, and then that's how I'm going to draw my gradient. I'm going to put the values. This is going to be 4 and 0.22 right here, and this value is definitely 0.38, and in the y-axis it's -4, so -4 and 0.38. Now let's figure out the gradient value. This 4 minus 4 divided by 0.22 minus 0.38. So this is going to give us a value of minus 50. So the reason behind this minus is because we have calculated the gradient of this line. If we did calculate the gradient of this line or this line, then this value would have come as only 50. So there is nothing to worry about this minus sign. You can just give the final answer like this, 50 meter per second. This will give you the whole mark. So that's basically how we figure out the maximum velocity. Now let's move on to the next part of the question. In part C, it says explain how damping causes the amplitude of oscillation of the car body to decrease. So guys, here you can see I will displace this mass. It will happily oscillate like this. It is reaching the maximum displacement every time. I mean, it is displacing with the same magnitude every time, because right here now the friction or resistive force is 0. So now what I'm gonna do is I'm going to increase the friction or the resistive force. Now look at this. The amplitude of oscillation has decreased, right? The amplitude of oscillation is decreasing. This is basically what damping is, because now it is doing work against resistive force and energy is transferring to the surrounding. Now guys, we all know during damping, energy is transferred from the oscillating body to the surrounding. And why? Because work is done against resistive forces, right? So that is going to be our answer. The question number 16 says a food delivery company uses ice packs to keep food cold during delivery. Each ice pack consists of a block of ice in a waterproof bag. Each block of ice is initially rectangular as shown. So basically it's rectangular. Water at 0.0 degrees Celsius is frozen to form the block of ice. The block is then cooled to a temperature of -7.5 degrees Celsius. Guys, can you understand this part? Liquid water at 0.0 degrees Celsius is frozen to form solid ice. So that basically means state change. Right here, state change is occurring. And we know during state change, the temperature remains constant. And we use the formula del E is equals to ml, right? We are going to use this formula for the initial part. Now in the next part it says the block is basically the solid ice is cooled to temperature of -7.5 degrees Celsius. So after freezing liquid water to solid ice, it is further cooled to -7.5 degrees Celsius. So now there is a temperature change, and when there is a temperature change, we use the formula E is equals to mc del theta. The block is then sealed in the waterproof bag. Determine the energy transfer to form the ice block and reduce its temperature to -7.5 degrees Celsius. The density of the ice has been given. As soon as I see that the density of the ice is given, I can understand that they didn't give us the mass of the ice, and they have given us all the dimensions right here. So from them, I will actually have to calculate the volume of the rectangular ice. And we know that volume is basically equal to the cross-sectional area into length, right? The cross-sectional area is this cross-sectional area, which is a rectangle. And we know this part is 15 centimeter and this is 1.5. So I'm going to multiply both of them as it's a rectangle, the length into breadth. So 15 into 10 to the power minus 2 multiplied by 1.5 into 10 to the power minus 2, and along with that cross sectional area I'm going to multiply this length. So the length multiplied with the cross sectional area, so this gives me my volume. And as I have calculated my volume, the value will be 5.63 into 10 to the power minus 4 meter cube. So now I've got my volume and I have also got the density. So using both of them, I can calculate my mass. As I know, density is equals to mass by volume and mass is equals to density into volume. And I've got the mass of the ice is 0.518 kilogram. Now guys, the next part is the total energy transferred. The energy is first transferred to freeze the liquid ice into solid ice, and then further energy is transferred to reduce the temperature. Okay, so the total energy transferred will be equal to energy transferred to freeze the water plus the energy transferred to cool the water to minus 7.5 degrees Celsius. Okay, so energy transferred to freeze the water is going to be del ml. Okay, and energy transfer to cool the water is going to be mc del theta, and that change in temperature is from 0 degrees Celsius to minus 7.5 degrees Celsius. Okay, so we know E is equals to mc del theta plus ml. So these are the two formulas that we are going to use. This is for mc del theta and this is for ml. Okay, so here I'm going to put the mass and then the specific heat capacity from here multiplied by the change in temperature, which is from 0 degrees Celsius to 7.5 degrees Celsius. This is the change, right? And then we multiply the mass of the ice with the latent heat of fusion of water. This is basically the energy transferred to freeze the water. So that's the value. And then we will add both of them to calculate the total energy transferred to reduce the temperature from 0 degrees Celsius to minus 7.5 degrees Celsius. So that is basically the total energy transferred. I'm going to put the value as 1.8 into 10 to the power 5 joules. The website of the delivery company includes the following statement. If the ice has melted by the time you receive your delivery, this means that energy from the ice has been used to keep the food cold. Explain why the statement made by the company is not correct. Now guys, this statement is wrong because it is saying energy from the ice has been used to keep the food cold. Ice doesn't give out energy when it melts. I mean, to melt the ice, energy must be supplied to it, right? In the form of latent heat. And this energy will either come from the food or from the surrounding, which means the ice basically absorbs heat from the food, keeping the food cold as it melts. Okay, therefore it is not the ice giving the energy, but instead the ice is taking the energy from the food. And that is basically the explanation you should be writing. Hopefully you guys can understand it. In the question number 17, they have said the Gaia globe is a three-dimensional model of the earth as shown. So that is basically the Gaia globe that they are talking about. The inflated globe is suspended from above and is able to rotate. So this Gaia globe is basically able to rotate. The globe is filled with nitrogen gas. When fully inflated, the globe has a radius of 3.5 meter. So basically this globe has a radius of 3.5 meter. All right, I'm going to annotate this thing because it's going to be important. Never ever forget to annotate while solving question papers. It's very helpful, guys. Trust me. In the next part of the question, they have said, calculate the mass of nitrogen gas needed to exert a pressure of 1.12 into 10 to the power 5 Pascal inside the globe at a temperature of 22 degrees Celsius. So they have given us the pressure, they have given us the temperature as well. And look at this, guys. These type of questions are very common. They have asked us to calculate the mass of gas needed, and they have given us the mass of a nitrogen molecule. The formula is like this. The total mass of nitrogen gas is equals to the number of nitrogen molecule multiplied by the mass of one molecule. Okay, so we have got the mass of one molecule. We have to figure out the total number of nitrogen gas. So to figure out the total number of nitrogen gas, we need the number of nitrogen molecules required to exert a pressure of 1.12 into 10 to the power 5. Okay, so for this we'll have to use the formula PV is equals to nRT. Now Right here, they have given us the pressure, they have given us the temperature, but they didn't give us the volume. But they have also given us the radius. The radius is given to calculate the volume. We know this is a sphere, right? And the volume of a sphere is 4 by 3 pi r cube. So I'm going to use this formula to calculate the volume of the globe. 4 by 3 pi, this is my radius into cube. This will give me my volume value. So I've got my volume. Now using this volume value, this pressure and this temperature, I can easily figure out the number of nitrogen molecules. So that's how I can figure out the number of nitrogen molecules, because I know PV is equals to nRT, right? So I'm going to make N the subject. So it becomes PV divided by RT is equals to my N. So this is my pressure, this is my volume, this is my temperature, and this is the R value. So using this, I can easily figure out the number of nitrogen molecules. As I have got the number of nitrogen molecules and I know the mass of one nitrogen molecule, so now I can easily figure out the mass of nitrogen gas needed to exert a pressure of 1.12 into 10 to the power 5. So I will just multiply the number of nitrogen molecules multiplied by the mass of one molecule, and this is basically the mass of nitrogen gas that is basically required to exert a pressure of 1.12 into 10 to the power 5 Pascal inside the globe. Now in part B of the question number 17, it says the globe rotates with an angular velocity of 2.76 into 10 to the power minus 2 radian per second. Calculate the time taken for the globe to make one complete rotation. Now guys, they have given us the angular velocity and have asked us to calculate the time. We know there is one formula which relates both angular velocity and time. That is, angular velocity is equals to 2 pi divided by time taken, right? So they have asked us to figure out the time, they have given us the angular velocity. So we will just make t the subject of the equation, and it becomes t is equals to 2 pi divided by this angular velocity. So this will give us a value of 227.6 seconds. And I will give my final answer into 3SF, which is 228 seconds. It says a solid sphere has the same diameter as the Gaia globe. So it has basically the same diameter. All right. We have seen that the radius of the Gaia globe was 3.5 meter, right? So its diameter is going to be definitely 7 meter. Calculate the mass of the sphere that would give a value of G at its surface equal to 9.8 Newton per kg. Now guys, one formula that relates both G and diameter is G is equals to Gm by R squared, right? This formula includes both G, mass, and the radius. Now right here, they have basically asked us to calculate the value of the mass that will give the gravitational field strength of 9.8. So I'm going to make this 9.8. I know the radius, I know this G constant value. I'll have to just make M the subject of the equation. So M is equals to GR squared divided by G. 9.8, 3.5 squared, and then this G value. This mass of the sphere will basically give the G as 9.8. So our final answer is going to be 1.8 into 10 to the power 12 kg. Easy peasy lemon squeezy question. The question number 18 says, the Hertzsprung-Russell diagram shows the relationship between the luminosity and the surface temperature of a range of stars. The Sun is a main sequence star. Label the position of the Sun on the diagram with letter S. So we know the Sun has a luminosity of 1 and it has a temperature less than 6000. So if the Sun has a luminosity of 1 and a surface temperature less than 6000, so it is definitely going to be right here, right? So let's just write it down like this. Here it will be S. You will have to write with the letter S. Now the next question, it says, in the final stages of the Sun's evolution, it will become a white dwarf star. Yes, exactly. We all know that. Draw on the diagram a possible path of the Sun as it evolves to a white dwarf star. Okay. So initially the Sun is on the main sequence, and then from the main sequence, it basically turns into the red giant, and then from the red giant, it evolves into the white dwarf star, right? So this is basically the evolutionary path of the Sun. The part B of the question number 18 says, Describe the stages in the evolution of the Sun from a main sequence star to a white dwarf star. So now, let's say this is our Sun. So there is gravitational force acting on the Sun inwards. Okay. Hydrogen is fusing in the core of the Sun. So as the hydrogen is fusing in the core of the Sun, there is a radiation pressure because of it. Now, the radiation pressure is basically equal to the gravitational force. Okay, but as more and more hydrogen is fusing in the core of the Sun, the number of hydrogen molecules available decreases. So the rate of fusion decreases. As the rate of fusion decreases, what happens is this radiation pressure decreases, and as the radiation pressure decreases, now the gravitational force is greater than the radiation pressure. And when the gravitational force is greater than the radiation pressure, the gravitational force basically dominates. And as the gravitational force dominates, the Sun contracts under the gravitational force, because right now the gravitational force is greater than the radiation pressure. The temperature of the Sun increases, the helium fusion starts. And when the helium fusion starts, at that time the radiation pressure increases. And then again, the radiation pressure becomes greater than the gravitational force. At that time, the Sun expands. It becomes this big. Now again, the number of helium atoms in the Sun decreases and the rate of fusion decreases. When helium fusion eventually stops and no further fusion takes place, this outer layer are lost and the remaining core collapses into a white dwarf star. And this is how we are going to write it. We are going to write hydrogen is being fused in the core of the Sun. When hydrogen in the core is used up, the rate of fusion decreases. The core collapses under gravitational force. Temperature rises high enough and the helium fusion starts. The Sun expands into a red giant. When no further fusion takes place, the star collapses into a white dwarf. Now in part C of the question number 18 it says, explain why the Sun will stay on the main sequence for a much greater time than the most massive main sequence stars. Now guys, to answer this question, we'll have to look at this thing. We know this whole part is the main sequence, right? The Sun will be somewhere right here. So the Sun has smaller temperature compared to the most massive stars who have very high temperature. Temperature of the Sun is less compared to the most massive stars in the main sequence. So the rate of fusion in the most massive stars is going to be very high as well. Now if the rate of fusion is very high, then the hydrogen in the most massive stars are going to get fused very quickly, right? Whereas the Sun has a smaller rate of fusion compared to the most massive stars. So the hydrogen fusion or the rate of hydrogen fusion is going to be a little less compared to the most massive stars. That's why the Sun is going to stay on the main sequence for a larger time compared to the most massive main sequence stars, because the rate of fusion of hydrogen in the most massive main sequence stars is very high. So the hydrogen is going to get used up quickly and they are going to get converted into a red giant very soon compared to the Sun. So this is going to be our answer. Most massive main sequence stars have much higher temperature than the Sun. Hydrogen is fused at a greater rate than in the Sun. So the time spent on the main sequence is going to be less compared to the Sun. Tau Kt is a main sequence star similar to the Sun. Several planets orbit Tau Kt. The spectrum of electromagnetic radiation emitted by Tau Kt has a maximum intensity at a frequency of 5.5 into 10 to the power 14 Hz. Show that the surface temperature of Tau Kt is about 5300 Kelvin. Now guys, as the question asked us about the surface temperature, there is only one formula in astrophysics which includes surface temperature. This is this formula, which is lambda max T is equals to 2.898 into 10 to the power minus 3, right? Now they have asked us to calculate the surface temperature. And to get the surface temperature, we need the maximum wavelength. Now this lambda max is basically the wavelength at which the maximum luminosity occurs. And in the question, they have said the maximum intensity was emitted at a frequency of 5.5 into 10 to the power 14 hertz. So they have given us the frequency. So we'll have to convert this frequency into wavelength. So that's how we use it. So we'll use the formula C is equals to F lambda. From there, we will convert the frequency into wavelength like this. We know wavelength is equals to the speed of light divided by the frequency that they have given us. So now we will use this wavelength right here to calculate the surface temperature like this. And I will write my final answer as 5310 Kelvin. The next part of the question says, calculate the average kinetic energy of gas atoms at the surface of tau kt. Now guys, there is a formula of average kinetic energy, right? Which is half mc square is equals to 3 by 2 kt. And this temperature is basically the temperature that we have figured out just a couple of minutes back. So we are going to use that temperature value right here to calculate this average kinetic energy. So my average kinetic energy is going to be 3 by 2. I know the K is a constant, and that temperature right here will give me my average kinetic energy value as 1.099 into 10 to the power minus 19 joule. So that's it. Now guys, this is a very important concept which I always teach my students during the class. That is, let's say light from the sun is incident on the earth. So when the light is incident on the earth, the light is incident from the sun. So the sun has its own radius. Okay. And the light that is incident on the earth from the sun also has this distance. This is the distance that the light travels to be incident on the earth. Now there is two formula. One is luminosity is equals to 4 pi r squared sigma temperature to the power of 4, and intensity is equals to luminosity divided by 4 pi r squared. Okay, now there are two r in these two formulas, but where we are going to put which one? Luminosity is basically the power output of the sun itself. So to measure the power output of the sun itself, we'll have to take the radius of the sun. So that's why whenever you will be figuring out luminosity is equals to 4 pi r squared sigma temperature to the power of 4, at that time in that radius you will have to use the actual radius of the sun itself. And intensity is equals to luminosity divided by 4 pi d square basically also includes a radius, and that radius is basically the distance from the earth to the sun. So please remember this thing, and you can put this value right here in the luminosity portion as well to calculate the intensity of light incident on the earth. Okay. Now in the part B of the question number 19, it says Ita is a planet in orbit around tau kt. A scientist suggests that Ita receives the same intensity of light from tau kt as the earth receives from the sun. So they are basically comparing the intensity of light that Ita receives from tau kt with the intensity of light that earth receives from the sun. Okay, now they have already given us the intensity of light received at the surface of the earth. This was basically a mistake that the Edexcel made themselves, and they did rectify that as well. So this is going to be earth rather than Ita. So this is basically the intensity of light that the earth receives from the sun, and we are going to compare this intensity of light with the intensity of light that Ita receives from the tau kt. So to compare it, we will actually have to figure out the intensity of light that Ita receives from tau kt, and we will use the formula intensity is equals to luminosity divided by 4 pi d squared. And we know that this distance is the distance between Ita and tau kt, right? We have seen it a couple of minutes back. So they did give us the distance between Ita and tau kt as well, so we can put it right here. We just need this luminosity, and this luminosity will be the luminosity of tau kt. Now to calculate this luminosity, we are going to use the formula luminosity is equals to 4 pi r squared sigma into temperature to the power of 4. We have already calculated the temperature, right? And this radius is basically the radius of the tau kt itself, just like the way we have seen a couple of minutes back, right? So we are going to put this formula right here, and then we are going to figure out the intensity, this formula divided by 4 pi d square, and this distance is basically the distance between Ita and tau kt. So that's how we use the formula, and the value that we are going to get is 2120. which is basically greater than the intensity of light received at the surface of the earth. So we can say that the suggestion is incorrect. The question number 20 says the space probe Galileo was sent into space to study the planet Jupiter. The space probe was powered using plutonium 238. Alright. Plutonium 238 decays to an isotope of uranium by emitting an alpha particle. Complete the nuclear equation for the decay of plutonium 238. Now guys, in order to complete this type of nuclear equations, the first thing that I can see right here is an alpha particle. And I know that an alpha particle has 2 protons and 4 nucleons. I mean 2 protons, 2 neutrons. So I have drawn it like this. Now the plutonium has 238 nucleons, and if alpha particle has 4 nucleon, then uranium will definitely have 234 nucleons, right? Because 234 plus 4 is equals to 238. So I'm going to put 234 right here. And if the proton number of uranium is 92 and the proton number of alpha is 2, and then I'm going to add both of them, which is 94, is basically the proton number of plutonium 238, right? That's how the game unfolds. Now in part B of the question number 19, it says the space probe was powered by the energy released in the decay of plutonium 238. Show that the energy released in the decay of one nucleus of plutonium 238 is about 5.7 mega electron volt. Now guys, in radioactive decay, the total mass of the decay products, which is basically the uranium and alpha particle, is going to be less than the mass of the original parent nucleus, plutonium, right? And this difference in mass is basically the mass defect. So let's figure out the mass defect right now. So now what I'm going to do is I'm going to subtract the mass of alpha particle plus the uranium nucleus from the mass of plutonium nucleus like this, and I will get the mass defect as 1.01 into 10 to the power minus 29 kilogram. And they have asked us to show the energy released. So I'll convert this mass into energy by multiplying it with c square. And this is the energy value that we have got. And this is the energy that is released. But this energy is in joule. But they have asked us to show in mega electron volt. So I'm going to convert it into mega electron volt. And that's how we convert it into mega electron volt. And the value that I'm going to get is 5.68 mega electron volt. When the space probe was launched, the decay of plutonium 238 produced a power of 550 watt. A website states that there was 1 kg of plutonium 238 when the space probe was launched. Deduce whether the website statement is accurate. Now guys, we will have to check whether 1 kg of plutonium 238 was able to produce a power of 550 watt. So to calculate the power, we will have to use the formula power is equals to energy into activity, right? Now, the first thing that we will have to do right now is to calculate the activity. And we know the formula of activity is lambda into n. And to calculate the activity, now we'll actually have to figure out n as well. Now what we can see right here is 0.238 kg of plutonium has this number of atoms. So as they're talking about 1 kg of plutonium, we can use the formula like this. If 0.238 kg contains 6 into 10 to the power 23 plutonium atoms, then 1 kg will contain this amount. So let's figure out the value. So the value is going to be 2.52 into 10 to the power 24 atoms. So this is the number of atoms that will be in 1 kg of plutonium 238. Now guys, we have got this n. Now to calculate the activity, we need the lambda. And we know T half is equals to ln 2 by lambda, right? And right here, if you make lambda the subject, it becomes ln 2 by T half. So they have given us the half-life. This is the T half. And we will actually have to convert it into seconds. So 87.7 years I mean, 1 year is 3.15 into 10 to the power 7 seconds. So 87.7 years will be 87.7 multiplied with 3.15 into 10 to the power 7 seconds. And now we have got the lambda as well as the number of atoms. So we can easily calculate the activity like this. And the value of activity is 6.33 into 10 to the power 14. Right? Now we have got this activity. Now we are just one step behind calculating the power. So now to calculate the power, we need the energy. And we did calculate the energy in the previous part of the question, right? So now let's figure out the power using that energy, which was 9.09 into 10 to the power minus 13 joule. So we have calculated the power as 575 watt. And as this power is very close to 550 watt, so we can say yes, the statement was accurate. The space probe took 74 months to travel to Jupiter. Calculate the power produced when the space probe arrived at Jupiter due to the decay of plutonium 238. Now, guys, they have asked us to calculate the power produced, and we know the formula of power is energy into activity, right? Now, as he is going to travel for 74 months, the activity is definitely going to decrease, right? So does the power. The power will also decrease, but the energy released per decay will stay the same. Okay, because each nucleus of a radioactive isotope will always release the same fixed amount of energy when it decays. Okay, the only thing that changes is the activity, and if the activity changes, that means the power will also change. Now let's have a look at this thing using an example. Now guys, let's have a look at this example. Let's say the initial activity is 2 into 10 to the power 12. Now if I have to calculate power, I will multiply this activity with the energy, and let's say the energy is 3 into 10 to the power 12. So I will get the power as 6 watt. After 10 seconds, let's say the lambda has become 0.1. So as the lambda has become 0.1, the activity will also decrease, right? So does the power. So let's figure out the new activity. We know activity is equals to a naught e to the power of minus lambda into t. We provide the initial activity like this right here, e to the power of minus lambda, I mean the new lambda multiplied by the t because of 10 seconds. And then we get the new activity as 7.36 into 10 to the power 12. So using this new activity, now we can actually calculate our new power. So while calculating the new power, the energy is going to be the same. Okay, but the activity did decrease. So now this is our new power, which is 2.21 watt. So rather than doing such huge things to calculate the new power, we can actually use this formula. Power is equals to P naught e to the power of minus lambda into T. We know that our initial power was 6 watt. I will put that 6 watt right here into e to the power of minus lambda into T. The new wavelength is 0.1, which is in 10 seconds, and we get the same 2.2 watt. So we can use the formula P is equals to P naught e to the power of minus lambda into T. And this is exactly the same formula which we will use to do our math. Hopefully you guys have understood the example that I've given. So we can use the formula P is equals to P naught e to the power of minus lambda. This is the lambda value that we have figured out into time. So this is for 1 month, and we know there was 74 months. So 74 into the seconds in 1 month will give us the new power value. Now in the next question it says, Jupiter is much further away from the sun than Mars is. A space probe to Mars was powered by solar cells. Suggest why solar cells were not suitable for a space probe traveling to Jupiter. Okay, now guys, I mean, the Jupiter is much further away from the sun than that the Mars is. So we can use the formula of intensity, right? Intensity is equals to luminosity divided by 4 pi t square. And the intensity basically depends upon the distance, right? And here you can see the sun. And let's say the Mars is right here and the Jupiter is right here. So the Mars is very close to the sun, whereas the Jupiter is very distant from the sun. So as the Jupiter is very distant, the distance from the Jupiter to the sun is very high. So the intensity is going to be very low, right? So that's why the intensity incident on the solar cells will be very small because the Jupiter is very distant from the sun compared to the Mars.